Now that we know the limit laws for the basic limit results, sums, differences, constant multiples, products, etc., we can come to a very nice conclusion about polynomials. Now, polynomials are special functions that follow a format that looks like the p of x function you see on the screen. The c with a subscript n or n minus 1 or 1 or 0, those are coefficients. The x's are the actual variables, and the exponents are n or n minus 1 or 1 or nothing at all. So a polynomial is just a sum of a bunch of terms that follow the same format. They can have a constant coefficient, they can have a positive exponent, positive natural number exponent. So we don't have any radicals here. We don't have any variables in a denominator. Pretty straightforward. So polynomials all follow this format. And if we want to investigate the limit of a polynomial, what we can do is apply our limit laws and see if we can find maybe a shortcut. So we'll start by applying the limit to our function, which means we're applying the limit to p of x and the limit to all of those terms that are being added together. And since we have the sum law for limits, we know that we can distribute that limit operator to every term in our sum. And we also have a constant multiple law, so the c coefficients can all be factored out of the limit operator. Next, we see that we have some exponents. We have a power law. If we apply that, we can, instead of taking the limit of x to the n, we can take the limit of x and then raise that to the nth power. So we apply our power law. Notice now that all of our limits have been reduced down to our basic limit results, the limit of the function x or the limit of a constant. And if we simplify these limits, we can see that the limit of x when x is going to a is just a. The limit of c sub 0, that was a constant, so that limit is equal to c sub 0. And notice now that we have what looks like our original polynomial where all of the x's have been replaced with a. That's essentially the same thing as evaluating your polynomial at the x value a. So when we talk about the limit of a polynomial of x, when x is approaching a, all we have to do is replace the x's with a's. We can do direct substitution. We can't do this with all functions. As of now, we only know that we can do it for polynomials. We'll learn later that if we can determine that our function is continuous, then we can use direct substitution to evaluate our limits algebraically. It's pretty nice. Let's take a look at some examples of what I mean by doing direct substitution for a polynomial function. The polynomial we're looking at here is 4x squared plus 2x plus 1. Notice that we have variables with positive integer exponents and coefficients, but nothing else, no crazy terms in this function. And when we look at the limit where x is approaching -2 for this polynomial, I'm now telling you just replace your x's with -2 and then simplify. Let's try another one. This polynomial is 3x squared minus 2x plus 4. It follows the format of a polynomial, so for the limit when x goes to 0, we just replace all of our x's with 0 and evaluate. Let's try another one. This time we're not using x as our variable, but don't let that fool you. It's the same concept. This time we're just calling the variable t. Our polynomial has some decimal coefficients, but notice that the variables still have positive integer exponents. So I don't have any decimals as the exponents. I don't have any negative numbers as my exponents. So we're still looking at a polynomial, but this time the polynomial is a function of t. And if we let t approach 0, then the limit of this function just looks like all of the t's being replaced with 1. I think I misspoke and said let t approach 0. I meant let t approach 1. That's the limit we're investigating. And if we simplify that, maybe we plug that into our calculator, we find that it's equal to 25 1/10, or 25.1.